Hi everyone, it's 1 p.m. Eastern Time sharp, and we have our regular webinar, Solver Colloquium, which is also joined today with Colloquium Institute of Space Weather at NJIT and also Physics Department seminar, so a joint event. Today we have a talk by Haimin Wang entitled High Resolution Observations of Solar Flares. And let me briefly introduce Haimin. Haimin obtained his bachelor's degree from Nanking University in 1982, then PhD degree from California Institute of Technology in 1988. Now he is Distinguished Professor of Physics in New Jersey Institute of Technology at and he is currently the chief scientist of Big Bear Solar Observatory and director of Institute of Space Weather Science at NJIT. He has published about 300 papers in referred journal, obtained about 10,000 citations. He is leading an effort in this interdisciplinary research of applying advanced machine learning to analyze big data from solar observations. He trained over 20 PhD students, led many US, NSF, and NASA funded projects. And today we have his talk on high resolution observations of solar. So please go ahead. I will send you a warning 5 minutes before.
Okay, thank you very much, Gregory. So today I'm going to share some of the observations in recent years on the solar flares. It's only one basic question on the resolution and the cadence, what solar flare would look like. It's not only the solar flares themselves, but the atmosphere around it, and as well as the triggering mechanism of it. So that's the basic question. So the most of the present observations are done at Big Bear Solar Observatory with the 1.6 meter Goody Solar Telescope. So now it's achieving a resolution around 0.05 arcsecond. The field of view is limited to a little bit less than 100 arcsecond. So with this resolution, we can resolve pressure scale height, which is 150 kilometers in the photosphere, and also the mean photon mean free path. DKIST can achieve higher resolution. So I will show a comparison in the next slide. So this is provided by Professor Wenda Chow. So as you all know, the DKIST has obtained the first light. This is from their press release. And we compare their image with a typical image at Big Bear, which at this moment is a resolution around 20 kilometers versus a Big Bear 30 kilometers. So as you can see, the DKIST, basically the GST can capture all these structures as a DKIST would do, but DKIST structure appear to be sharper somehow. And so this is our assessment. Due to a larger aperture, the DKIST can have a higher resolution at its best seeing that lasts a shorter period of time. And also because of the larger collecting photon collecting area, so the polarization accuracy would be significantly higher when the adaptive optics can lock. So GST, on the other hand, has a good and stable seeing lasting for hours during the day. So it's critically important to follow targets such as flare productive active regions. So our conclusion is GST is not replaceable by DKIST, in particularly in the research of solar flares. So our conclusion is DKIST and GST are highly complementary in achieving a lot of science goals. Okay, so if we talk about the highest resolution observations, I believe the very first paper back to almost 20 years ago by Jess, they used the Swedish 1 meter telescope to observe wildlife flare. As you can see, they magnify that from left to the right, and the size of the flare kernel is around half arc second. Okay, with this resolution, it's a 1 meter telescope, and it achieved a sub-arc second resolution, obviously. Their contrast is 300%, so it's a very bright kernel. So in that paper, they said when we have enough resolution and enough cadence, almost all the flares probably would be wildlife flares. So since they observed a flare with magnitude of C 2.0, which in today's standard is quite small. So that was the conclusion they had. But up to now, after observing of dozens of the flares, with probably all above 2.0 at Big Bear, and we cannot confirm this. We found that it's still very, very hard to observe wildlife flares, even with the resolution of the GST, which is higher than the resolution of the Swedish telescope. Okay, the very first high resolution observation of the flare was published by Sharikin and Kosovichov in 2014. This is the H alpha off band. So you can see from what my cursor is pointing, the flare ribbons appear to be extremely narrow. They said it's around 100 kilometers. So this is possible by can be resolved by Big Bear GST. And in the earlier time, with the high resolution, we immediately can detect a lot of things, not only during the flare in the chromosphere, like H alpha. From left panel, you can see the structure of flare ribbon. Then during that 2 hours from 18 UT to 20 UT, you should be able to see substantial change in photosphere as well. Due to the flare, there was nothing between those two sunspots. So after the flare, the penumbra formed. They actually formed rapidly. So this is a kind of so-called back reaction of the solar flare. I will mention some part of that later. Okay, and also we immediately can see in with the high resolution. I'm going to skip to this one. Usually we see the flare as 2 ribbons, and this publication we had, we immediately see the 3 ribbons. So there are 2 loops and share a common polarity right here. And we can see the structure really well. And with a low resolution, we probably will show as a compact flare. With a high resolution, we can see 2 loops back to back. This is a kind of resolution. This is the kind of structure we did not see before. And then we produce this concept, which is still debatable. I'm not going into the detail. You have polarity inversion line here, and there are 2 loop systems. And here we construct a called a non-line instead of non-point. But anyway, so this is all due to the high resolution observation. We can disclose such a fine structure. Okay, and then we show the process of the flare eruption, and we can identify twisted flux loop very clearly. And one thing here, we will see, this is one of the press release of NGIT when we catch the flare, is the structure is fragmented. You can see individual threads in the fiber structure. And if you run as a movie, you can see the eruptive process of it very clearly, how the twisted flux loop coming out from the sun, and also those twisted loops consist of a lot of threads. They have the fine structure. Then we, of course, we use the coronal field extrapolation method. We can identify the extrapolated field structure coincides very well with what we found in H alpha. So this is a powerful tool to look at both magnetic structure with extrapolation and also with the high resolution observations. Okay, so this is one of the flares received a lot of attention. I just want to point a few things. This is an event. I will show a few other results. So the description of that flare was published in Nature Scientific Reports by Jin. So first, you will see before the two ribbon flare appeared, there are two precursors. So I will mention those just a little bit later. The one, second one, and then flare happens. And another thing is this is a post-flare loop. It's very high speed flows. In a post-flare loop, what you can see is because of downward motion, there is secondary brightening. If you follow my cursor, you will see when material streaming down, and this is first the brightening flare ribbon. In the later phase, there are little brightenings at the foot point. So that's due to for the post-flare loop, material streaming down, then kinetic energy becomes heating. So that kind of observations were not shown in the lower resolution observations before. Yeah, although it's similar to some of the concept in the EUV observations as a coronal rain, but we now shown with very high resolution. And the last thing I want to point out is the fiber structure. I will mention some of the concept in the end of the talk. They are really fine structure in a post-flare loop. So that indicates reconnection in very small scale. Although, we can present a flare as an ensemble, but they may consist of a lot of small scale energy release. And the size of those post-flare loops, as we shown here, is around 100 kilometers, which is similar to the previous study of the flare ribbon width. It's in the order of about 100 kilometers, which we never seen before until we are using this Big Bear telescope. Okay, I just want to show one thing that's specifically interesting to the Drive Science Center members. It's about the reconnection speed. For this flare, I will show the movie right after this. There is a light bridge. The light bridge has a weaker magnetic field. Then you can see the flare ribbons will propagate slower when the field is weaker. So this movie will show this propagation of it. So you can see in the light bridge, the flare ribbon will move faster. Then should it this statistical analysis, you can see very clearly the B field, when that's stronger, V is smaller, the ribbon propagation speed. When B is larger, V is smaller. So then B times V probably is a constant. And we know B times V is actually the electric field strength. So you have a uniform electric field strength that make the ribbon motion different with different B field. Okay, Now that it's the same flare, I will show one kind of interesting thing that was published by Chang Liu in Nature Communication. So there is a famous saying about the dog versus the tail. The people think the corona or the upper atmosphere, because the density is much lower. So they call that part of the atmosphere is called the tail. The photosphere, the density is high and not easy to move, of course. So it's called the dog. So usually dog wags the tail. The wagging of the tail cannot change the dog. So that's been an interesting question. We previously showed some evidence wagging tail can change the dog's position. There is some physical interpretation, especially by Hugh Hudson and George Fisher. So I'm not going to talk about detail of that part. It's been that kind of discussion been going on for a long time. So what we show here is a movie. If you follow this yellow box, so you can see sudden motion of sunspots. So this motion did not cause the flare, but on the other hand, the flare caused the sudden motion. So it's a wagging tail caused the dog to shift. Okay, so again, in that paper, we also used the concept of Hugh Hudson, George Fisher, to understand it. It's change of Lorentz force, and this time is the torque. The torque can make the rotation. But anyway, this movie also shows the capability of Big Bear observations. If you watch this movie, actually I only show about 2 hours or 2.5 hours of that. You will have a feeling it sounds like it's observing from the space, but actually it is observed from Big Bear. You have very stable atmosphere for few hours a day. So that's why you can catch the entire process of the flaring active region. Okay, and in that paper, we demonstrated it's not the rotation caused the flare. Immediately after the onset of flare, the sunspot starts to rotate. And the rotation angle has to be, it's as a function of time. It's plotted here. So it's very clearly demonstrated the solar flare can cause the sunspot to shift with such a high resolution. Then in a previous study, we saw another kind of phenomena. After the flare, the fields are collapsed into the photosphere. That's a different story. That was done in our group by using the HMI data. But this is the first time we see such a clear evidence the flare can cause the rotation of sunspot. Its interpretation, although we have kind of physical understanding, but there is no simulation to explain this phenomena yet. Okay, so this is what I already showed. Okay, and the next part of the talk is the flare triggering. Okay, with the highest resolution, now we should be able to look at the flaring polarity inversion line in a great detail. So this actually was motivated by several studies of the group in Japan, of the Kusano, Professor Kusano. And he been looking at the triggering of the flux in solar flares in the small scale, we understand the energy buildup and eventually CME involving a much larger space. And the small scale motions may not play an important role in the energy storage or the eventual or the energy release of the flare. But there are a lot of evidences those small scale reconnection can cause instability, therefore trigger the flare. So this kind of the flare triggering might be important to understand or even forecast the possible onset of the flare. So this is a comparison of the different observations. We have a simultaneous observations from Big Bear, from Hinode, and from HMI. It's obviously we are observing similar thing, same thing. The Big Bear has a higher resolution. In an earlier paper, actually a couple of papers, including Zirin and myself in a Nature paper, we did point out that in a higher resolution, you are no longer be able to define a polarity inversion line as if you have a positive sunspot, negative sunspot, anything in between could be very complicated. So we call that magnetic channel structure. And this is one of the examples. And you can see under the high resolution, I mean, from left and right, the same sequence of Big Bear magnetograms. The only difference is we enhance the contrast on the right side. Then you have this kind of complicated structure. You cannot identify positive or negative. So we did a very careful analysis. That work is published in Nature Astronomy. We found that the flux cancellation triggered the precursor of the flare, therefore trigger the entire flare. And we also found that during the triggering process, the electric current density enhanced substantially. You have the local enhancement of electric current, and the flare is set off first as a precursor, and the main flare occurred in the same location. Okay, and we are also using expanded Owens Valley radio array. At that time, for the observation, we did not have imaging capability. So now the eOVIS can do the imaging spectroscopy. At that time, we used the power law, total power to derive several important parameters. One of them is the magnetic field of the flaring source. Since the precursor, it's very much concentrated. Just from basic physics, we can see this so-called turnover frequency in the microwave decides the magnetic field strength. When this one is getting shifted to high frequency, you have higher B field, and to the left, the lower B field. So although it's quite noisy, but we can see the flare initiation started from kilogauss field. So that means the flare initiation starts from near the photosphere. So this is the power of using Owens Valley data together with Big Bear data. Both are the NGIT facilities. Then I just want to show one slide. This is what we also found for the very famous active region, September 6, in September 2017. And using the Big Bear data, we can use the, we don't have to use a Stokes inversion. We just use the basic Zeeman splitting to measure the distance between separated Zeeman component. then we found the B field is one of the historical highs, around 6,000 Gauss. So there are later papers described even in a corona, this active region produce 1 or 2,000 Gauss field. So this is, and this is a very unusual active region. And in the photosphere, we think there is evidence of twisted flux loop. But this is still under, I mean, we need to still process the data. At least we found unusually strong upflow on those points, but this still need to be resolved. Okay, now let me shift to a different kind of phenomena observed by our Big Bear telescope. It's called a negative flare. When we talk about the flare, everybody knows that means brightening, okay? But there is a special line in the solar atmosphere, that we use to study the sun. It's called a helium 10A30 line. And I know some of the audience are the PhD students. So you have a qualifier in a few months. So this could be one of the good qualifier problem for the quantum mechanics. So for the helium, there are 2 electrons. The spin could be parallel to each other, opposite to each other. If they are parallel to each other, then you have a total spin of 1, then you have triplet. So that means your projection of the spin can be positive, negative, 1, and 0. And if you are 2 electrons in opposite spin, then your total spin is 0. So that's called a singlet. For the helium, most of that are in the, the default state is the called perihelium. They are the 2 electrons are in the opposite spin state. So normally all the electrons are here. So for the 10A30, you need to use called author helium. So that's a spin is 1. So it won't get to here unless there have a process you ionize from the single state helium, and then they have a recombination. The ionization can be done in 2 processes. One of the 2, one is by collision, the other is by heating in ultraviolet, by the really photon ionization from the ultraviolet photons. Okay, so that's why it was, this should be a movie. Let me see. Just for some reason, the movie doesn't play. But anyway, I probably will have a movie in a later slide. At that time, I will show that again. Let me see if I can get it in a, okay. Okay. I apologize for some reason. Oh, okay. This is the same movie, so I will go back to that. So just watch this movie. This is a propagating ribbon. It's a flame. Okay, okay, so it's running again. If you watch the flare ribbon, you will see that in front of it, there is a dark band. That dark band, the width is also a sub-arc second. So that's called the 10A30 absorption. Let me go back to what we have before. Okay. So that was the, if you make slit there, do a so-called time distance plot. So what you will see is as time going on, in the 10:30, you have propagating. So this is a time and this is a space. You have a propagating ribbon, which is dark. And there is an earlier study, we used the D3, it shows a similar thing, but this is the first time we show in the 10:30. And trailing that, it's bright, okay? Then we do the same thing for the AIA, that's the UV observation of the SDO. Then we can see there is no absorption. It's just a propagating of the flare ribbon, just all the brightening. Okay, how about if you fix one space point to plot the intensity as a function of time, so you clearly will see a dip in, this is like couple minutes after starting of the flare, you can see a dip. It's just, it takes time for ribbon to get to there. And you also see there is a second dip, although it's not absorption. At that time, we thought it's measurement error, but later on, we found that actually it's not, okay? So this is the concept of the so-called the dark ribbon. It was predicted by Professor Ziering, but this is the very first time it was observed with such a high resolution. Then we also compared with the iris observations at the same flare. Then we found for the positive flare, the line profile, that's the magnesium K line and H line, they are the normal profile. For negative flare, they have a self-absorption. But again, in the iris observation, it's never dark ribbon. It's just in the line center, there is a dip, okay? So now I'm going to show, I need to do this part very quickly. This is from the PhD thesis of Renyi Huang. She just defended her thesis like a couple of months ago. And if you need to know the detail, you can discuss with her. She uses the modeling to explain the two phenomena, okay? So I just make this one to be quick. The one phenomena is what I just showed, the dark ribbon flare in 10:30. Another phenomena is about the blue shift and red shift, the sequence of blue shift and red shift of the solar flare, like in the line, such as H alpha line. So conventional wisdom is the when flare electron come down, you see red shift because that's an electron moving towards you if you're observing the sun. And then when energy accumulated enough, it has an evaporation, then you're going to have a blue shift. And in a couple of events, not only this one, some other author published it as well, you actually have three components. One is you started with a blue shift, and then red shift, that's electron coming down. And finally, you have the evaporation, that's blue shift again. So, but anyway, she uses, that's a very standard code, so I'm not going into detail. And also using a web modeling tool to input the parameter from our observations from RESI, and also the size of the flare kernel. I just want to mention here that one significant thing that we are detecting, the flare kernels are much smaller than what people predicted. So the flux density becomes much higher, just due to, you have a smaller area, but still same energy. So that changed the modeling a lot. Then she explained this sequence. In her modeling, you really can see the redshift in the very beginning. And I'm sorry, the blue shift in the very beginning, followed by red shift, and finally the blue shift again due to the evaporation. Again, so that's in her thesis, also published recently in APJ. And another important thing is this, what I already explained, so-called absorption. And remember that we thought there is a dip. That probably was our measurement error. When she ran the code, this is what she ran based on the parameter again. It's a little bit of exaggeration. We didn't see such a huge jump, but in principle, let's look at the modeling result. It's absorption, then there is a second dip. And my guess is, although we're looking at it in more detail, the first one is due to collisional ionization and the recombination of the 10A30. The second dip probably is due to enhanced photoionization, since at that time, your thermal component becomes more important than there is a second photoionization in addition to the first collisional ionization. So this is what still we are trying to understand what's going on. But at least we are glad we did not remove this dip. We put it there, and it seems like the modeling can explain this second dip in 10A30 light profile. Okay, now let's talk about another physics problem. So this is probably also can motivate a lot of discussions. As we know that both electrons and the protons probably accelerated high up somewhere during the reconnection process. But the electrons are lighter, much lighter than the protons. So naively, we would think the electrons at probably finally they are all neutralized. In a certain short period, the electrons are streaming down. So there is a charge separation. So you have a streaming down of the electrons to the surface. And when you have a flare ribbon, it's like you have a wall with strong current. So this could be another good qualifier problem. If you have the strong current and what you have induced the B field. Then with some calculation, you will see this induced B field would be parallel to the solar surface. So temporary, you would make the B field direction change. So that was the scientific motivation of this study. We want to see if we can detect this temporary B field change. So this should be a, let me see, oh yeah, this should be a movie. And if you look carefully, just follow my cursor, you will see this is, it's not a B strength, but it's just a B field direction. So you can see a propagation of a disturbance. It is, there is when this actually corresponding to a flare ribbon. If you could argue, would that be caused by the emission? No, because Stokes I did not change comparing to the background at a different time, and did not change the line of sight field as well. Okay, but it changed the Stokes U and the Stokes Q. There are two parameters to measure Bx and By. That's the direction along the surface of the sun. Okay, so we know it's not due to the emission. So we thought we explained the problem, but when we look at the two ribbons, we found explain one ribbon and could not explain actually the opposite effect of another ribbon. So, but anyway, in that paper, we did describe what we think, but what we failed to explain. But this remained to be an unexplained phenomena. The linear polarization changes when the flare moving across the surface. Okay, so finally, I just want to show in the high resolution.
Ayman,
Yes.
you have around 5 minutes.
Oh, okay. I think I have 3 more slides. Should be
Okay.
able to finish. Okay. So when we you know the sun is quite it's very quiet. So actually, this might be a good timing to look at the small events. So this is one of the very small flare. It's actually, I look at a GOES catalog. It's not even classified as A class flare. So it's very small. If I run the movie in H-alpha, okay. So H-alpha is a little messy. If you follow my cursor, you probably will see a little brightening. This is a 1 foot point. And then there's another foot point that barely you can see. So those kind of flares are very small phenomena. If you do a subtraction, you can see those flare kernels very well. And you can see the weaker one, even a weaker tail, it's like that. In the previous 1030 slides, I did show that when flare happens, in the 1030, you can see the individual fibers coming out. I just want to show for this one, we also had a 1030 observations. Okay. If you pay attention, in 1030, you cannot see flare, neither absorption or emission, because it's so tiny. But in H-alpha, you can. But in 1030, just follow this one. A lot of fibers covering the 2 flare foot point, but right before the flare, they're all gone. You want to look at a certain period, then they become, yeah, they pretty much become clear up. So there are 2 possibilities. One is heated up, the other probably more likely. Those small fibers, they move up, interacting with fields above. That creates a flare ribbon. So that going back to the previous mentioning, so the flare process may involve a bunch of small-scale magnetic reconnection. Okay, although when we treated CME, it's a large-scale phenomena, but during the process, there could be a lot of small-scale reconnection happening. And so I just want to mention this during the, it's almost 40 years ago, some of us probably remember, there's a SMM mission, Solar Maxima mission, and using the instrument called a Hexpers, whatever that was, the Kiplinger, they pointed out there are a lot of so-called elementary bursts. Actually, that's a common phenomena in the SMM observations. The lifetime, this is some magnification of some of the events. The lifetime sub-second, okay? So I just think with Big Bear observation and also future possibly decreased observation, we can look at a flare with high resolution and high cadence. At this moment, our cadence is reduced because we need 100 frames to do speckle reconstruction. But there might be some other more advanced technology only use a few frames. Then if we have even higher cadence, then we might be able to combine the spatial resolution and high cadence, identify those so-called elementary bursts observed almost 40 years ago. Okay, so here's my concluding remarks. The first, I just want to repeat that GST and DKIST are highly complementary, and GST is especially important for flare observations and also the observations around the flares. The flare ribbon pre and post flare loops are in a scale about 100 kilometers. So that's a size that we can resolve with big bear observations. And in 10A30 and also D3, we do detect negative flares. There's a very narrow dark front that can be explained by modeling as well. And the fourth item is we do find an irreversible rapid photospheric magnetic structure change. And the one I show is a rapid sunspot rotation in our observation. So finally, is the filament eruptions may consist of the rising of many small-scale threads, and that could be corresponding to a small-scale brightenings in chromosphere. They may be linked to the concept of elementary flare bursts as what people found from hard X-ray 40 years ago. Okay, thank you very much.
Thank you, Jaime, for excellent timing and very informative and dense talk with a lot of fundamental phenomena covered. Now we're open for questions and comments. Just I propose who has a question, please unmute yourself, but try to speak in order.
Yeah, this is Brian Dennis. Can you hear me?
Oh,
yeah,
hi, Brian.
Go ahead, Brian. Yeah.
I just wanted to tell you that the instrument you're talking about is the hard X-ray burst spectrometer on SMM.
Oh, yeah.
And had said that was pronounced Hexabris.
Oh, Hexabris. Okay.
Yes, that's the official pronunciation. But in fact, that's the first detection of elementary flare bursts. There's something that I think Peter Hoying and Frank Van Beek had talked about, and De Jager earlier than that.
Oh, okay. So I probably missed that one. I only quoted Kiplinger's APJ letter paper.
Right. Yeah. That was a later.
That's a later one. Oh, okay. Okay, that's good to know.
This is Spiro. When you say that the ribbon fronts and the flare loops are a scale of 100 kilometers,
yeah,
you think that you've resolved the structures, or is that just the 100 kilometers is coming from limits of GST?
The GST, our resolution, if I can show you the this plot, let me see. It's there is a plot of the we made a plot across the fiber. I think we resolved it. You can see there are many points.
I see. Okay.
Yeah.
It's also very interesting.
If you only have 2 points, then you said it could be still unresolved.
So you think you've got the scale?
Yeah.
So you think you've got the scale of the reconnection, because presumably each reconnection event, because that's 100 kilometers. The other thing that's very interesting, is that the loops that I see are so parallel to just so laminar that again tells us something about the reconnection.
Yeah, right. We discussed it the other day, right? Yeah, I didn't see any twist. That's a question.
Right.
Yeah, right.
Very nice.
A comment about the width. Yeah. I think it would be hasty to say that they're actually resolved, because it's optically thin and you have foreground background effects, and so this is not a three-dimensional kind of image.
Okay. Yeah, that probably. So when we get to DKIST, if we get this kind of, you can get maybe twice better. So I don't know if it will make a fundamental difference.
Well, the theorists always want to get the scale for reconnection. I'm just saying that probably it's still an upper limit kind of thing.
I see. Okay.
Yeah. Also, a comment about
observers for years now, so hopefully we'll get it.
Never. Also, a comment about the the loops being so sort of laminar and parallel. Jaime, these are basically post-reconnection loops, is that correct?
Actually, these are the post-flare reconnection loops.
Okay, so we don't know anything about.
There is a set of loops perpendicular to this set. They are also laminar, and they are rising up. That's those set of the loops Spiro was talking about.
I see.
Yeah.
Okay.
So there are two sets. One is post-flare. Those are crossing polarity inversion line. And there is a parallel set of the loops. They are rising along the polarity inversion line.
But none of them look particularly twisted, although they could be very sheared.
We only saw one event that we can see that's S shape that come out. That's what we saw. But for a number of events, this is something bothering us. The flare coming from, so Spiro called that laminar, the loops, they are rising, then interacting with arcade loops, then creating the post flare like this.
Okay. I also had a question as well about your measurement of the using EOVSA of the magnetic field strength as a function of time, and about your interpretation.
Yeah, that's the this one. Yeah, right.
Yeah, that one. So your interpretation there. I mean, the reconnection or the flare starts in kilogauss field, and then the strength decays. So do you have a kind of geometrical interpretation?
Since at that time, the EOVSA did not have the spectrum, images spectroscopy. So we were not able to get really 3D topology. But probably I didn't explain that clearly. So those are not the flare itself. If it's a flare, it's extended source is too difficult with total power. So those are the flare precursor. That means the initial brightening. There are two of them, and they come from the kilogauss field. Since EOVSA data is sensitive to detecting the brightest, source, you can find the B field on that brightest of that brightening. So that's an advantage of it.
Okay, thank you.
All right.
Fantastic data.
Hi, Hemming, can you hear me?
Yes.
Yeah, so I just follow up on the precursor phase thing. You shared a lot of excellent observations. It's exciting, and I don't have a chance to look at the details. But could you elaborate on the so-called precursor phase? From your observations, can you tell where is the energy release of the precursor phase? Is it in the concentrated area, or is it along the flare entire ribbon? And also,
from our highest observation, it happened to be exactly, it's not necessary to be strongest gradient or strongest shear. It's the highest dynamics. So if in the movie you can see that a lot of motions and flux cancellation in this area.
So you mean it's at the same location as the initial flare ribbon?
Yes, yeah, right. They all come from this area. It's a very small area.
But how about the length? Is it along the entire ribbon length or just in a small area?
In a small area, very, very concentrated area. So you probably saw this new paper by Kusuna in Science that come a couple of weeks ago. He did that even further with some concept that I haven't digested yet to demonstrate. He used this to predict the location, the initiation location of the flare. He said he predicted very well.
All right, thank you.
Okay, I see in the chat, Judy Carpin has a couple of questions or comment. Judy, would you like to unmute yourself and deliver these questions and comments?
I'm sorry, I have some noisy stuff going on in the background, so that's why
that's absolutely fine. We hear you well.
Hi, Judy. Yeah.
Hi. So just a quick question on your second conclusion. Do you mean the loop length or the width is 100 kilometers?
Width. Yeah, loop width. Yeah.
The width. Okay.
Yeah, right. Yeah. Sorry, I should have put the loop width. Yeah, right.
Okay. Yeah. No, thanks. That's very interesting. And I just wanted to point out that actually OSO 5 saw elementary bursts before SMM did. Brian knows that too. But I think Hoing also. Anyway, it's a minor point. Thanks.
And we saw this again with the BEST, the gamma ray observatory. And we did not see that much in the RESI, right? Probably because of the cadence. So anybody can make a comment? Yeah, we saw that in the BEST of the GIO. And
Yeah, RESI only had basically 4 seconds time resolution.
Oh,
so
okay. So maybe that's why. Yeah.
I think that's the problem.
So where the new instrument just got selected, that there was a hard X-ray instrument.
No, I don't think so. I don't think that's
okay. So we don't have anything can do a high cadence.
Unfortunately not.
But we do have eOVSA, so we are using that, since that can get milliseconds of the cadence. So that's
Jaime, there is Fermi and there is Conus wind with spectral and time resolution, but no spatial resolution. No image.
Yeah, right.
There will also be
for this, what I show here did not have a spatial resolution either. They identify the time, the different bursts, so that we can try to link into spatially resolved features by GST or DKIST.
There will also be sticks on Solar Orbiter.
Oh yeah, so that can. What's the cadence there, sticks?
Gosh, I don't know.
Okay.
I think it's comparable to RESI, but maybe somebody online knows better than me.
Yeah, I think it might be better than RESI. RESI has 4 seconds for full imaging, but we have sub-seconds for time resolution. And I think there's a paper by Zhang Xu on detection of small microbursts.
Oh, okay.
RESI. But you have to do special sort of analysis to remove the modulation.
Oh, yeah, right. Yeah, actually, I'm the co-author of that one. I forgot about that paper, yeah.
Right.
This is Hugh. I think there's a question here about these time variations that Kiplinger discovered. So we know there are also time variations that George Parks discovered, which are what we call the QPP. Now, and these have time scales of a few seconds to tens of seconds.
QPP has a certain periodicity, right?
Well, roughly. And so I'm just wondering how these rapid variations fit into the QPP pattern, which is quite universal. I think the rapid variations here are fairly infrequent. Brian may want to comment about that, but the QPP happen in almost every flare.
I see.
But Hugh, but those are longer. It's about 10 seconds.
I agree. 18 seconds was what Parks saw. That's how it sort of hangs in there.
Yeah, we didn't do QPP analysis, but this plot you're showing here on the right-hand side looks to me like it's got some real QPPs in it.
I see. Yeah, right. It's a periodic.
But they're very short period, I think, aren't they?
Right.
Looks about a second or so.
So those QPP were related with some wave phenomena, right? It's like oscillation. So.
Well, some of them in the later.
Not necessarily.
Not necessarily. Okay.
Phase, it's not,
Yeah.
If you're Nakaryakov, it's waves.
yeah, no, but not in the impulsive phase. I don't believe it's waves in the impulsive phase.
Well, that's the claim.
Yeah, I know. But the later phase, I think the case is much stronger for waves.
Okay, guys. Any other comments or questions?
Yes, I have.
Please go ahead.
Jaime, on the question you showed this result where the speed of the ribbons was inversely correlated with the magnetic field strength.
Yeah, right. Yeah, that one
kind of...
I believe. Let me see. Let me try to get that one.
It's actually never published. I thought that it was well known that when the ribbons first start, they move very fast, then they slow down. So if I look at one event, it looks as if it's directly correlated. But you're saying if I look at different events, I get the inverse result?
This is from a single event. And also I would say during the period it had almost a uniform motion. So this one also only demonstrated during the short period of time. If you have a strong field, it moves slower. If you have a weak field, it moves faster.
But so when do you have the strong field? Is that at the beginning of the event?
During that period, it was moving across this entire sunspot. So I wouldn't tell which part is stronger.
Spatial pattern.
Starting, from right to the left. So actually, the middle part is strongest.
Mm-hmm.
Yeah,
I
that's
think more generally, what people have seen, myself and Zhongchu included, and Hai Min has been involved in this work as well, is that the product of the product of the V and B is strongly related to the hard X-ray variability.
Oh yeah, right.
Given flare, in a given flare, there's not really any system. I've never seen anything particularly systematic about the relationship between B and B themselves. But maybe you need to look in kind of in more detail, more spatial detail, as has been done in this paper.
It's an interesting result, very, very important result.
Yeah.
Because
Actually the reason there is a non-uniformity, you see this part of the light bridge,
right?
It's a weak field. Then we see a kind of acceleration because the field is weak, so it moves faster along this light bridge.
When you say weak field, what do you mean? Vector field, total?
Actually, both vector for the light bridge, the total B field is much weaker than surrounding.
I thought that usually in light bridges you had stronger fields.
No, actually, for at least for this one, you have a much weaker field. That's the light bridge across. This is a light bridge in the same polarity. Light bridge I mentioned later, it's opposite in delta sunspot. Then you're right, it has a strong field.
So can
both light bridge and umbra dots have a weaker field.
So this is Jim Drake. I'm trying to ask, I guess, about that interpretation of the VB relation. If one had reconnection at some rate in the corona, then if you're looking at the foot point motion, then you would see a varying foot point velocity depending on what the strength of the B is, just because if you have a constant flux annihilation in the corona, then V would vary depending on what the strength is at the foot point.
Yes, precisely. I think that's the interpretation. You have a fixed reconnection rate in the corona. And then if the B is stronger, that means it's at a unit of time, it goes through a smaller area.
Okay, guys, we are in the second hour already, so I propose like the most important questions or comments, and maybe last ones, if they're available.
Can I ask Brian? Brian, you made some comment about a paper which looked at high time, short time events. Could you tell us what that reference is? I couldn't quite hear what you said.
It's Zhang Xu.
Actually, I can find that one. I can email to you since I'm.
That would be. This is Jim Drake. Yeah, that would be very helpful. I'm really. Yeah. We're trying to see these high variability things because we're trying to figure out whether it's possible that that's revealing something about, for example, flux ropes forming during the reconnection process. So this kind of thing I think is really important.
Okay, I will email you. There are, believe a couple of papers, as Brian mentioned. We use a demodulation provided by Brian, and that way we get a higher cadence. So now I recall that paper.
Gordon Burford, not by me, but the concept of elementary flare bursts was introduced, I think, by de Jager in the 1980s.
Oh yeah, okay. The same de Jager who is the solar physics editor.
Yes, exactly.
Okay.
It's from the what happened before SMM. I can't remember its name, but they had an X-ray instrument on the spacecraft before SMM. That
OS something.
No, not OSO, not OSO.
Also, okay.
I can't remember what its name was.
Or the one Japanese one, the
There was the Dutch,
That Hixus,
No,
was it
also-
Hixus?
that's-
HXIS?
SMM, it was the instrument, the imager on.
Hixus, I think.
Yeah, that was the Yaga's instrument on SMM, but it was before
okay.
that.
Yeah, I'm sure
Oh,
I
sorry.
will be able to find that one. So.
Rather recently, Lindsay Glessner and I published a paper about flare in a jet, which showed clear sub-second evolution, sub-second structure in X-ray. So it was 2019. Other questions or comments? It seems no other questions or comments. So in this case, I can close the meeting, close the event. So thank you very much.
Thank you.
Thank you very much,
Thank you.
all
Thank you for-
participants. I can mid of October is next talk. Thank you. Bye bye.
Okay, bye.
Right.